Hello students, in the previous class we discussed about few basic concepts related to the heat as well as temperature. So in this class we are going to discuss about specific heat. So let us first revise what are the things which we have already discussed in your previous bridge course classes. So first heat we all know that it's a form of energy. Heat always flows from a region of higher temperature to the region of lower temperature. Whenever there is a difference in temperature, heat will flow. It always flow by convention. Heat always flows from region of higher temperature to the region of lower temperature. Next, SI unit of heat is joule. Next, temperature. Temperature is the what? Degree of sensation of hotness or coldness of a body. It is a degree of hotness or coldness of a body. When heat is supplied, the temperature of the body increases, and when heat is removed, the temperature of the body decreases. The SI unit of temperature is Kelvin. So we will use a device which is called as a thermometer in order to measure the temperature, and also we studied that we will use normally we use different types of scales in order to measure the temperature. For example, Celsius scale, Fahrenheit scale, as well as Kelvin scale, and also it is also possible to convert the temperature from one scale to the another scale. Next, states of matter. So we all know that the matter exists in our nature in three states. They are nothing but solid, liquid, as well as gases. Next, in this chapter we are going to discuss about a few concepts related to this: specific heat, degrees of freedom, law of equipartition of energy, as well as latent heat and calorimetry. Next, specific heat. So in the beginning only I will tell, whenever heat energy is supplied to any substance, two things are possible. Either there may be increase in temperature, or there may be a change in what? State. If there is no change in state, then the temperature of the body increases. If there is no change in temperature of the body, then there will be a change in what? State. So for example, solid to liquid, as well as from liquid to gas. So how much quantity of heat is required in order to raise the temperature of 1 gram of a substance through 1 degree Celsius? In order to increase the temperature of a body 1 gram, 1 degree Celsius, how much heat is required? What quantity of heat is required? That will be indicated by a constant or a term which is called as specific heat. So specific heat means the quantity of heat required to raise the temperature of unit mass of a substance through unit temperature. In order to increase the temperature by 1 degree Celsius of a substance having unit mass, how much heat is required? That is nothing but specific heat. Quantity of heat required to raise the temperature of unit mass of substance through unit temperature. So there is an experiment which indicates on what factors the specific heat of a material depends. Usually specific heat depends upon the nature of the material. Its value is different for different material. So what are the factors on which the specific heat depends? In order to understand that concept, I am going to conduct a few experiments. First one, so consider two beakers. Both the beakers contain same quantity of water. So next, on those two beakers, different quantity of heat energy is supplied. Then what will happen? Observe. So now here there are two beakers. The diagram shows two beakers. Both the beakers contains equal quantity of water, that is 400 ml. Both the beakers contains a thermometer which is used to measure the temperature. So for the first beaker, for the beaker A, two burners are provided. Large quantity of heat is supplied, and for the beaker B, there is only one burner, which indicates less quantity of heat energy is supplied compared to the previous one. What does it indicate? What is the inference? So after conducting this experiment, you can conclude that temperature in the first beaker is more than that of what in the second beaker, because more heat is supplied to the first beaker as usual. So for the first beakers, large quantity of heat is supplied. So and hence obviously the increase in temperature is more in beaker A compared to the beaker A. So the quantity of heat supplied is directly proportional to the what? Change in temperature. Delta theta represents the small change in temperature, where Q indicates the quantity of heat energy supplied. That is, Q is directly proportional to delta theta. Next, in the second experiment, so I will consider another two beakers, X and Y. One is half filled and another one is completely filled with water. So here also there are two beakers, one is half filled while another one is completely filled. Now supply the heat energy so that they attain the same temperature. Once again I am going to supply certain quantity of heat energy for those two beakers so that final temperature attained by the both the beakers should be the same. Final temperature attained by the liquid in those two beakers should be the same. So then what does it indicate? Observe the quantity of heat energy supplied in this case. So here one beaker contain 50 ml of water, another beaker contain 100 ml of water. So if both the beakers should attain same temperature, for that you should supply different quantity of heat. Therefore, as mass increases, the quantity of heat supplied should also increase. Quantity of heat is also directly proportional to the what mass of the substance. One beaker contains less amount of water, another beaker contains large amount of water, which indicates if you want to raise the temperature by equal amount, so the quantity of heat energy supplied should be different. Therefore, quantity of heat energy supplied is also directly proportional to the mass of the substance. So now I am going to write a formula for what? Specific heat. So now combining all these terms, in the first experiment you come to know that Q is directly proportional to the delta theta, and after conducting the second experiment you come to know that Q is directly proportional to M. Combine those two terms, you can write Q is directly proportional to delta theta and it is directly proportional to M also. So in terms of a constant of proportionality, you can write Q is equal to C into delta theta into M, where C is equal to Q divided by delta theta into M is called as specific heat. The quantity of heat required to raise the temperature of a unit mass of a substance through unit temperature, that is called as specific heat. Its SI unit is, so Q is the heat energy, SI unit is joule divided by delta theta, temperature Kelvin, so mass unit is kg, therefore SI unit of specific heat is joule per kg Kelvin. Next, another experiment, third experiment. This is to illustrate how Q value depends upon different materials. So as I said earlier, Q value depends upon the nature of the material. Its value is different for different materials. So keep 4 different balls. One is made up from copper, another one is from brass, bronze, as well as aluminium. They are having the same mass and they are heated to the same extent. They are placed in hot sun for few minutes. So touch the balls and feel their hotness. So now what you are going to observe, different balls are heated to different extents since the nature of the material is different. Therefore, the quantity of heat absorbed by each and every ball is also different, and one ball may be more hotter when compared to the other balls. Different balls will have different hotness. This is due to the fact that heat absorbed will be different for different materials. So as I said earlier, specific heat value depends on depending upon the nature of the material. Therefore, obviously, the amount of heat absorbed by the ball will be different. Heat absorbed will be different for different material. That is, they have different values of heat capacities, which are nothing but specific heat. Next, the table shows the value of specific heat for different materials. For example, for aluminum it is 0.9, copper 0.39, ice 2.05, iron 0.45, lead 0.13, silver 0.24, while for water the specific heat value is 4.19. What this indicates? The specific heat value of water is very large when compared to the other metals. What does it indicate? Water takes more time to heat as well as what? More time to cool also. So that's the inference. Since the specific heat of water is very large, it takes more time to heat as well as what? It takes more time to cool also. Next, specific heat capacity of gases. So till now what we are discussing that is nothing but specific heat of solids. So in case of gases, we know that when heat energy is supplied to the gas, there may be a change in what? Increase in pressure what? Increase in pressure as well as what? Increase in volume also. If the pressure is kept constant, there will be increase in what? Volume, and if you kept the volume constant, then there will be increase in what? Pressure. So when heat energy is supplied to the gas, the pressure also increases as well as what? Volume also increases with respect to temperature. If the pressure is kept constant, volume increases, and if the volume is kept constant, then the pressure increases. So correspondingly, we have two specific heat for gases. Gases will have two specific heats. One is specific heat of gases at constant pressure, and another one is specific heat of gases at constant volume. So when heat is supplied to the gas, temperature, volume as well as pressure will change. Hence, we define two types of specific heats. They are specific heat of gases at constant volume to the specific heat of gases at constant pressure. Next, specific heat of gases at constant volume. So, how to define specific heat of gases at constant volume? It is the quantity of heat required to rise the temperature of unit mass of a substance through 1 degree Celsius, keeping the volume constant. So, for example, if you consider a cylinder which is fitted with a movable frictionless piston, so here volume should be kept constant. Now it is enclosed cylinder, piston is not provided. Supply the heat. When you supply the heat, then what will happen? Here volume is kept constant. Then what will happen? Pressure is going to increase. That's it. So quantity of heat required to raise the temperature of unit mass of a substance through 1 degree Celsius, keeping the volume constant. Next, similarly, specific heat at constant pressure. In this case, for the same cylinder, attach a movable frictionless piston. So here volume is not kept constant. In order to keep the pressure constant, the piston will move in which direction? Upward direction. So therefore, what will happen? The pressure remains constant. So since volume is not kept constant, so in order to keep the pressure constant, volume gets changed. In this case, the quantity of heat required to rise the temperature of unit mass of a substance through 1 degree Celsius, where the pressure being kept constant. Next, comparison Cv as well as Cp. Cv means specific heat of gases at constant volume, where Cp means specific heat of gases at constant pressure. So differentiate these two now. So Cv has lesser value when compared to Cp. Heat, in case of Cv, heat absorbed is utilized only to rise the temperature, while in case of Cp, heat utilized for doing the work and also to rise the temperature. As I said earlier, when the volume is kept constant, for example, if you consider a closed cylinder, when you supply the heat, since the volume is kept constant, all the supplied heat energy is utilized to increase the temperature only. Therefore, Cv has lesser value. Why? In case of Cp, so pressure should be kept constant. Therefore, for the same cylinder, a piston is attached. Now, in order to keep the pressure constant, when the heat energy is supplied, the piston moves in which direction? Upward direction. So thereby pressure remains same. Therefore, large quantity of heat is required. In this case, the heat required is utilized not only for increasing the temperature and also to perform the work also. Next, why Cv is greater than Cv? As I said earlier, so in case of Cv, all the heat energy supplied is utilized to increase the temperature only. But in case of Cp, heating the gases at constant pressure, a part of the supplied heat energy is utilized to perform the work done. Remaining amount of heat energy is utilized to increase the temperature. Why work has to be performed? So piston has to move in which direction? Upward direction. Why it has to move in upward direction? In order to keep the pressure constant. So the piston has to move in upward direction when the heat is supplied. So thereby pressure remains same. Therefore, Cp is always greater than Cv. Heat absorbed at constant pressure is utilized for two purposes: to increase the temperature and to increase its volume to perform the external work, whereas heat absorbed at constant volume is utilized only to rise the temperature. Therefore, Cp is always greater than Cv. How they are related? Cp and Cv are related by an equation which is called as Mayer's relation or Mayer's equation, that is given by Cp minus Cv is equal to R, where R is a constant which is called as universal gas constant. R is always having a positive value. Therefore, Cp minus Cv should always give us a positive value, which means Cp is always greater than Cv, or Cp minus Cv is equal to R is called as Mayer's relation. Next, degrees of freedom. So, in case of solids, in between the molecules as well as in between the atoms, there exists a strong intermolecular force of attraction, a strong interatomic attraction. In case of liquids, the intermolecular force of attraction is less when compared to the solids. But in case of gases, the intermolecular force of attraction is very less. What will happen if the intermolecular force of attraction is very less? So gas molecules are moving randomly. So because of what? Weak intermolecular force of attraction. So if you want to indicate this, if you want to specify the position as a position of the gas molecules, we need degrees of freedom. So degrees of freedom are nothing but a Cartesian coordinate system. For example, whether the gas molecules moving randomly in all the possible direction, whether it is moving along the x-axis, whether it is moving along the y-axis or along the z-axis. In order to indicate the position of a gas molecule in space, we require a Cartesian coordinate system. That Cartesian coordinate system is nothing but what? Degrees of freedom. It is the minimum number of independent coordinates. The minimum number of independent coordinates required to specify the position as well as motion of a gas molecule in space. I repeat once again, it is the minimum number of independent coordinates required to indicate the position as well as what? The motion of a gas molecule in space. So it is the number of independent variables required to specify the position of a particle in gas. This depends upon the number of atoms present in the molecules of a gas and also their orientation. For example, we know that there are three types of gases. First one is monoatomic gas, which consists of a single atom; diatomic gas, which consists of two atoms, as well as what? Triatomic gas, which consists of three atoms. So degrees of freedom is different for different types of gases. For example, if you consider a monoatomic gas, in case of a monoatomic gas, there is a single atom. It can move along the x-axis, it can move along y-axis, it can move along the z-axis. Then how many degrees of freedom are required? Only 3 degrees of freedom are sufficient in order to indicate the position as well as what? Motion of a gas molecule, monoatomic gas. For example, if you consider a diatomic gas, O2, oxygen, then 2 atoms are there. So how many degrees of freedom are required? In this case, totally 5. Why means, so 2 atoms, they can move together, they can move along x-axis, y-axis as well as z-axis. 3 degrees of freedom are required for translational motion, and another 2 more are required for what? Rotational motion. They can rotate in their own axis. So therefore, for diatomic gas, degrees of freedom required is equal to how much? 5. For triatomic gas, degrees of freedom is equal to 6 or 7. That depends upon what? So whether the molecules are linear or non-linearly arranged. So therefore, degrees of freedom will be different for different gases. Why we have to consider degrees of freedom? In order to indicate this, in order to specify the position as well as what? Motion of a gas molecule in space. Next, you studied about Cp as well as Cv. The ratio of Cp to Cv, the ratio of specific heat of gases at constant pressure to specific heat of gases at constant volume is always a constant. That constant is called as ratio of specific heat. That is nothing but heat capacity ratio, gamma. Gamma is equal to Cp divided by Cv. There is a formula which relates specific heat ratio as well as degrees of freedom, that is given by gamma is equal to 1 plus 2 divided by 5 and 2 divided by F, where F is the degree of freedom. If you know the value of degree of freedom, then you can easily calculate the ratio of specific heat value for a particular type of gas. For example, you already know about that. You already know that for monoatomic gas, degree of freedom is 3. So substitute F value as 3 in this equation. Then 1 plus 2 by 3, that is equal to 1 plus 0.66, that is equal to 1.66. Therefore, the ratio of specific heat gamma value is 1.66 for which type of gas? Monoatomic gas. Gamma value decides whether the gas is monoatomic, diatomic as well as what? Triatomic. Next, law of equipartition of energy. So we know that according to the law of conservation of energy, the total energy of the system should always remain same. Energy can neither be created nor be destroyed, but it can be transferred from one region to the another region or from one form to the another form. So whatever the system is having the energy, that is equally distributed among its all degrees of freedom. For example, in case of monoatomic gas, there are only 3 degrees of freedom. All the total energy of the system is equally distributed among all of its 3 degrees of freedom. In case of diatomic gas, it has 5 degrees of freedom. The total energy of the system is equally distributed among all of 5 degrees of its freedom. So for a gas in thermal equilibrium, the total thermal energy is equally divided among all the degrees of freedom of a molecule of the gas. The energy associated per each molecule, the energy associated with the molecule per degree of freedom, half kBt or half kT. Whatever each degree of freedom contain how much energy? Half kT, where k is a constant called as Boltzmann constant and T is the absolute temperature. Next, change of state. As I said earlier, when heat energy is supplied, two things are possible. Either there may be increase in temperature or there may be change in state. When there is a change in state, the temperature remains same. During the increase in temperature, there is no change in state. Only one thing is possible at a particular instant of time. Two things are not at all possible at a single instant of time. During the change in state of a substance, the temperature remains same. During the increase in temperature, there will be no change in state of the system. What do you mean by change of state? So, for example, if you consider some ice bricks in a beaker, when you heat the beaker, when heat energy is supplied to the beaker, then what will happen? Ice melts into water. That means there may be a change in state from solid to liquid. That is nothing but what? Change of state. So we know that there are three states of matter: by the absorption of heat energy, by a removal of heat energy, by the absorption of heat energy, or by the removal of heat energy. The matter can undergo physical change from one state to the another state. It can undergo change from solid to liquid, or from liquid to gas, or from gas to solid also. That depends upon whether the heat energy is supplied or heat energy is released. So this diagram shows how the change in state phenomenon actually occurs. So for example, in case of solids, so if you consider ice here in a beaker, then what will happen here? When heat energy is supplied, then what will happen? Ice melts into what? Ice melts into water. That phenomenon is called as what? Melting. So again, during this change in state, the temperature remains same. So that is 0 degrees Celsius only. Next, again, when you heat the water, and again, if you want increasing the supplying the heat energy, then what will happen? The temperature of the water continuously increases. It reaches 100 degrees Celsius. Once the 100 degrees Celsius is reached, then what will happen? It gets changed into what? It gets changed into. So here, take some quantity of ice in a beaker. When you supply the heat energy, ice melts into water. That phenomenon is called as melting. Then again, if you supply the heat energy, then what will happen? So here, liquid state changes into the vapor state. That is called as what? Evaporation. Next, again, if you supply the when you remove the heat energy from vapor state, then what will happen? Vapor condenses into liquid. Again, when you remove the heat energy, then again liquid state changes into the what? Solid state, which is called as what? Freezing. So solid to liquid, melting; liquid to gas, evaporation; gas to liquid, condensation; liquid to solid, that is called as freezing. And also there is a chance of what? Conversion of solid to gas directly, that is called as what? Sublimation. The change of state from solid to gas directly, that is called as sublimation. Next, latent heat, which is nothing but the quantity of heat required to change unit mass of a substance from one state to the other state without any change in temperature. That is called as latent heat. As I said earlier, during the change in state of a substance, there will not be any change in what? Temperature. Temperature should remain same. For example, when you supply the heat energy to ice, then what will happen? It melts, it gets melted into what? It gets converted into what? Water. But during this change in state, the temperature remains same. That is how much? 0 degrees Celsius only. So that is nothing but what? Latent heat. Hidden heat. It is also called as hidden heat. The quantity of heat required to convert unit mass of a substance from one state to the other state without any change in temperature. It is represented by L. Next, I will conduct one more experiment here. Take some crystals of ice in a beaker. Note that temperature of the ice is how much? 0 degrees Celsius, around 0 degrees Celsius. Start heating it slowly at a constant heat source. Now draw the graph between the temperature and the time. So here there is a beaker which contains some crystals of ice here, which is attached with the thermometer, and here continuously heat energy is supplied. So now next, if you draw the graph of temperature versus time, the nature of the graph will be as shown in the figure. Here there are three or four regions actually. One is OA, AB, BC, as well as what? DE also. BC, CD, as well as D. So initially the matter exists in which state? Solid state. That is nothing but water contains some bricks of ice crystals are there. That is in which state? Solid state. Heat energy is supplied. Now what will happen? So all the supplied heat energy is utilized to increase the temperature. Hence we will get a what? Straight line. OA is a straight line. As the time increases, the temperature also increases. But the material exists in which state only? Solid state only. During the increase in temperature, the state remains same. During the change in state, the temperature will be changed. During the change in state, temperature remains same. During the increase in temperature, the state remains same. Here, there will be an increase in temperature. The matter exists in this state only, solid state only. Next, up to where it exists in solid state only, till the melting point is reached. After what will happen? Once the melting point is reached, then ice gets melted into water. So along AB, once the melting point is reached, along AB, what will happen? Ice starts to melt and it gets melted into water. So at this time, along AB, you can observe clearly the graph along AB, what will happen? There is a change in state from solid to liquid, but what about the temperature here? The temperature remains same. In this case, temperature remains same here. Only along OA temperature increases with respect to time. Along AB, what will happen? There is a change in state from solid to liquid. What will happen? The temperature remains same here. During the change in state, temperature remains same. Next, once all the solid gets converted into liquid here at the point B, thereafter what will happen? If further heat energy is supplied, the supplied heat energy once again utilized to increase the temperature. Here once again the temperature starts to increase. But what about the state? The matter exists in the state only, liquid state only here. During the increase in temperature, the state remains same. The temperature goes on increasing till where? Till boiling point is reached. Once the boiling point is reached, then what will happen? The liquid state gets starts to convert it into which state? Gaseous state. Here in this case, during the change in state, once again the temperature remains here. Same, how much? 100 degrees Celsius. Once, if each and every liquid molecule attains 100 degrees Celsius, then it gets converted into which state? Vapor state only. So next, once if all the liquid molecules converted into which state? Gaseous state, then it starts to evaporate. So once again, what will happen? If further heat energy is supplied, then what will happen? Temperature continuously increases, but the matter exists in this state only, gaseous state only. This is about the graph of what? Temperature versus time. So in the beginning, so when the heat energy is supplied, temperature increases, but the matter exists in this state, solid state only. When the melting point is reached, the matter starts to convert into liquid state, solid starts to convert it into liquid state, but the temperature remains same during the changing state. Once if all the solid gets converted into liquid, thereafter what will happen? Temperature once again starts to increase, but the matter exists in which state only? Liquid state only. If all the solid gets converted, if temperature reaches boiling point, that is 100 degrees Celsius, then what will happen? The liquid starts to evaporate. So this indicates there is a conversion from liquid to gas. So here also temperature remains same. Once if all the liquid molecules gets converted into gas, then once again, so the temperature starts to increase. So the graph is as shown in the above. OA represents the temperature increases till melting point is reached. AB represents temperature remains constant during the changing state. Temperature increases again up to boiling point. CD represents the temperature remains constant, but the water gets converted into steam. So AB, so along the curve AB, heat energy supplied is utilized for what? Change of state, that is from solid to liquid. So in the graph you observe there is a straight line which indicates there is a change in state from solid to liquid, which indicates supplied heat energy will be utilized to change the state of the system, but the temperature remains same. This heat is called as what? Latent heat of fusion. That is the quantity of heat required to convert unit mass of a solid completely into liquid at constant temperature. The quantity of heat required to convert unit mass of a solid completely into liquid at constant temperature is called as latent heat of fusion, that is called as LF. Next, along the curve CD, so there is a change in state from liquid to gas. So supplied heat energy is utilized for change of liquid state to the gaseous state. So that is called as what? Latent heat of vaporization. That is the quantity of heat required to convert unit mass of a liquid completely into solid gaseous state at constant temperature. That is heat utilized for conversion of unit mass of liquid into gas at constant temperature. That is called as latent heat of vaporization. Next, calorimeter. So we know that heat always flows from the region of higher temperature to the region of lower temperature. So when two different substances are mixed together, having different temperature, then what will happen? Hot substance loses the heat while cold substance gains the heat. That means heat energy will be transferred from hot substance to the cold substance. Till where? Till thermal equilibrium is reached. Thermal equilibrium means it is the state at which the temperature at each and every substance becomes, temperature of both the substance becomes same. That is called as thermal equilibrium. So when two different substances having different temperatures are mixed together, then there is a flow of heat from hot substance to the cold substance till thermal equilibrium is reached. That is called as what? Calorimetry. What about the principle of calorimetry? The heat lost by the hot substance is always equal to the heat gained by the cold substance. According to the law of conservation of energy, energy can neither be created nor be destroyed, but it can be transferred from one body to the another body, or from one form to the another form, another body. Here, whatever the heat is lost by the hot substance, equal amount of heat will be gained by the cold substance. That is the principle of calorimetry. Heat lost by the hot body is always equal to heat gained by the cold body. So we can conduct a simple experiment in a beaker contain some water. So heated metal plates, bricks are there inside the beaker. So what will happen if you continuously stir the mixture? Then what will happen after some time? It attains which temperature? Constant temperature. That means metal bricks loses the heat, so thereby cold water gains the heat. So next, two basic questions. Which of these causes severe burn injuries? Water at 100 degrees Celsius or steam at 100 degrees Celsius? And what happens if latent heat of ice is only 4 joule per kg? So try to answer these two questions. So in this class we will discuss a few important concepts related to the specific heat and specific heat of solid, as well as what specific heat of gases, as well as few important concepts related to the latent heat, change of state, latent heat of vaporization, as well as what latent heat of fusion, as well as heating curve in case of which indicates the change of state from solid to liquid, as well as from liquid to gas,